In this project, we're going to be making a task light or an LED lamp. Now, in this particular shop here, it's very well illuminated, but that doesn't mean I can see with great detail on smaller objects or things that I need to look at in a very precise way. For example, here on the drill press, I've got a task light there. Over on my bench grinder, I've got a task light. Over on my mill, a task light. Even the CNC router has its own lighting system. Now, even in a very well lit shop, that additional lighting right at the task helps you to see better and make better judgment with your eyes as to what you're trying to do. Now, historically, in machine shops going back since the beginning of electricity, there's been task lights, and back in the day, they used incandescent lights. And of course, an incandescent light gets very hot. So as a machinist over the years, you're working on something and inevitably your arm will touch the lamp, get a burn, and well, you just get used to it over time. Well, thank goodness LED technology has come a long way and they run much, much cooler. However, you still have to engineer into them so that they don't run too hot and get to the point where they can burn you again or fail or just simply self-destruct, as the case may be with overvoltage or overcurrent. For this project specifically, I'll be making these light fixtures that are going in a paint booth, which is another project that we've got on the YouTube channel here. It's over in the miscellaneous section. So if you don't have a paint booth, you may want to watch that video too. But what I needed was better lighting. My old booth was dark gray inside. It was like you were looking into a black hole. You just couldn't see any detail in the subject that you were painting. So one of the things that I really wanted was to have lighting inside the booth. And I wanted it to be variable intensity or variable brightness because as you can see, if you just got a little bit of light, that can help. Or perhaps you need more light, and again, that can certainly help. Or you can overblast it, and it's just simply too bright, and you can't see what you're trying to do. So I decided to go with variable power supply, and then 1-watt LEDs. Total cost is not that very expensive. The LEDs you can buy on Amazon for pretty darn cheap. The power supply, being a variable power supply, that's realistically your most expensive investment, but it certainly adds another feature to your lighting system that will help you, especially like in this paint booth. Some of the other ones you can go with direct voltage, as long as you don't push them too high on the voltage area. You can go with constant voltage and you'll be fine as well. Now to get started, for this project, I knew I wanted lighting that would come in at an angle on both sides of the booth, so it had to be a corner mount LED. And then the depth of it front to back, I had a length restriction there. I believe I needed it to be less than about 10 inches. And I had a rough idea how many LEDs I wanted in each one based on some of the other LED machine lights that I've built in the past. So with that information, I went into Fusion 360, designed up the enclosure. Once I had that figured out, that led to the ability to design the circuit board because we know the size and shape of the circuit board relative to the enclosure. And from there, we had to go into the electronics to figure out the current limiting resistors, etc. And then finally a lens for this, and then assemble it and get it installed on the paint booth. So here we're going to take a look at all those steps, and we'll go into greater detail on some of the things that may be not so common or something that you may not be comfortable with, and I'm going to walk you through those steps. So let's take a look. It's very important to select the proper current limiting resistors so that you don't put too much current through your LEDs and burn them out, or too much voltage, depending on how you look at it. Too much of anything generally bad for LEDs. Now for the LEDs that I use, which currently are not available on Amazon, we've got 3.1 to 3.3 volts and 350 milliamps. So I'm just going to use the max on both, 3.3 and 350 milliamps. Now my supply voltage will be 24, 3.3, 350 milliamps, and in total this lamp will have 14 LEDs. Click to calculate it, and it not only gives us a little schematic, our resistors, tells us that the nearest highest rated resistor for our parameters is 2.7 ohms, so that's what I ordered, slightly more than the exact calculation. And the total circuit current consumption will be 666. Ooh, that's an interesting number, 666 milliamps. And then it gives you all the rest of the, it's going to use up 300 milliwatts, so you need at least a half a watt resistor. You always got to watch this one on the calculator. If you're not familiar with current limiting resistors, you got to make sure you got one rated for enough current. But this tells you everything you really need to know. So going back to what will be your parameters if you order these LEDs that are currently available at the time of this writing, it'll be 3.2 volts at 280 milliamps. So we change that to 3.2 at 280. Click to calculate. 6.8 ohms would be the resistors for those LEDs when wired up in this configuration. Now what I usually do with this is I will start out with, say, my supply voltage, and of course these two parameters come from the LEDs. You can't really change that per se other than selecting a different LED. But to determine the amount of LEDs that I want, I start out, say I started out with 10. Click to calculate. 6.8 ohms, and then we kind of got an odd balance here. Not really what I want. Let's see, 12. Okay, with 12 we get an even split. 18 ohm resistor. It's got to be a 1 watt resistor, so it's got to. This resistor is going to dissipate a lot of energy. Total circuit is 533 milliamps. But to me this is a lot of waste going through. If I got to go that high of a resistor and I need to rate it for 1 full watt, it's probably going to be wasting energy. So if I go up a little bit higher, boom, now we're into a range where we're at a half a watt resistor. It's only using 376 milliamps or milliwatts, 470 amps. It's a little bit better in balance. And of course you don't need 2 rows. Maybe you're only doing 1 row. So let's go with 5. See how that calculates out. That worked out fine. 333 ohm resistor, etc. 6. We're still with 1 row. And that reason why selecting 1 row or 2 rows or 3 rows, the more LEDs that you have, the more the voltage drop is across all the LEDs. So we're going to get to this next one when we go to 7. I think we're going to still be okay. Yep, but when I go to 8, the voltage drop would be too much, and then now it has to start another row for you. So you can really tinker around with this and design lamps for the most part just using this little website. Great little place, but nonetheless, I would say put it in your library, bookmark it, and use this to calculate your current limiting resistors for your circuit. I'll be making this circuit board on my CNC router, one of my favorite tools. To hold the material to the router, I'm going to be using this Scotch brand double-sided tape. I picked this up at the office supply store. I found that it's a very consistent thickness and it works very well for this application. On my sacrificial board on the CNC router, I've got some previously machined marks in it, so I can easily align this board with an axis, either X or Y. Once I get it lined up, then I'll press it down. I'm going to put some weights on top of it so I get a really good adhesion between the circuit board, material and that sacrificial backer board. For the isolation engraving, where we mill around the traces, I usually use a V-shaped tool. This one's a 60-degree V tool. Very, very sharp. Comes to a wonderful little fine point, and it machines out grooves very nicely. For the milling of the outside shape, I use these types of end mills. They're very specifically designed for machining circuit boards the way we'll be using it. They got serrated flutes on it, and they cut nice and aggressively. And then finally, we'll be using an 1/8 inch diameter carbide drill bit to drill the mounting holes. I've made a mark on the circuit board where I want my 0 point to be in the X and Y axes. So with the tool in the spindle, I'm just going to jog over to that location, and I will select that as my origin point for the first circuit board. I'll be making 2 circuit boards out of this piece. Next up, I need to measure the tool length, and the way I've got my CNC router set up, I've got an automatic measuring thing, macro, in the control. So you hit the measure tool button, it'll move to a location where it wants to measure. It'll bring up another button for you to press. When you're ready, you hit that button, the tool comes down, touches the sensor, and automatically calculates the tool offset. Once I got that setup process pretty well done, the next thing to do is to load the program. Now the program I created for this particular circuit board is FlatCam. I start out in Sprint layout to create the geometry. I export Gerber files, import the Gerber file into FlatCam, and that'll help me create the G-code program. So I'll open that file up, and here we can see graphically what it's going to mill and how it'll mill it. And then we can go about starting the machining process by hitting cycle start on the machine. Now I believe at this point I'm running at about 18,000 RPM and probably 18 inches a minute going by memory. So it's a very slow feed rate. You don't want to really go fast. It's a very pointy little tool, so it can't really move very quickly. Now here you can see what it looks like after the machining is complete. You got nice clean traces. There isn't many burrs or anything, and what little burrs are left on the traces can easily be taken off with some fine sandpaper or a Scotch-Brite pad. The first one I milled without using dust collection, and I always try to machine fiberglass with dust collection to get the contaminants away, but when that's set up that way, you can't see what's going on. So here we're going to turn on the suck, and I've got my dust shoe on there for machining the second circuit board, and you'll see that that's a much cleaner operation. And here's an image of both circuit boards. Now we're going to go through and drill the 4 corners after I've loaded up the drill bit and remeasured that. And then finally, we're going to machine the outline of the circuit boards. Here I'll take a Scotch-Brite pad, knock off the burrs, polish the circuit board up a little bit. A putty knife helps me remove the circuit board from the sacrificial board on the CNC router. And then I'll peel off the double-sided tape and get rid of that. Finally, I'll break apart the PCB components, as I didn't mill all the way through. And then I'll clean up the edges with some sandpaper so I don't have any sharp edges. One of the complaints many people make about DIY circuit boards is the copper will oxidize over time, and realistically, sometimes it really doesn't take that long. Now, these particular blanks I've had in my shop here for probably in the neighborhood of 3 or 4 years, and they're fine, but of course conditions change. But I have found a product made by MG Chemicals. It's liquid tin, and I've been using it for years now, and it tin plates chemically the circuit board, and then of course that helps prevent oxidization. Process is simple, but they have an awful lot of warning labels on the bottles, so make sure you pay attention to all that. But we just simply put it in a container, pour the chemical over it, and let it sit for about 5 minutes, and you'll have a tin coating on the circuit board. And this is what they look like after tin plating. Now I gotta say, they're a little more mottled than I normally get out of this, so maybe my chemical's getting old, or maybe the boards were contaminated with oily fingers or something else from the shop. But generally they look more consistent like this. Now I would like to also mention that I don't throw away that chemical. I put it right back in the bottle from which it came, and then of course I clean everything per their instructions. But I've been using that chemical for a couple of years now, at least, and maybe it's getting tired, I don't know. But either way, that's what we end up with for our circuit boards that come off the DIY CNC router. It's a great process, very efficient, especially when compared to getting it made even in China. These really cheap companies that do it, they say overnight. It's going to be kind of hard to get a circuit board in 24 hours though, because you got to account for shipping and so forth. But either way, if you need circuit boards quick and you don't need super high fine detail like you would with very small surface mount components, this is a great process to use. I've found it much, much more reliable than the toner transfer and chemical process. Although when everything works perfectly in that process, I can get better detail. Okay, after the tinning process, now we need to move on to soldering the components on here. And as you probably already figured out, this is a surface mount layout, and the LEDs are surface mount LEDs. Now, I don't know how close I'm going to be able to get in on this so you can see what's happening. I believe this is about as good as it's going to get with my current rig. But all I'm going to do is heat up the leg while it's in place. These are the traces. This big pad here in the middle is kind of like a heat sink pad. We don't really solder there. We just solder in this area and back here. Now, as I showed you, this little leg here's got a plus sign on it. This one's got a minus sign. So minus is going to go toward our minus rail. Plus will go to our plus end. And then right here is where I would hook up the plus. So what we're going to do, I got my soldering iron up pretty close to max temperature. And the way I do this, I just center this on there as best I can. And then hopefully I won't twitch. Heat it and apply a good amount of solder once it heats up. And the first few take a little bit of work. Sometimes it'll jump like that. Usually that's me twitching a little bit. And then I'll just heat it up and recenter it. For the second leg, in this case the negative leg, that one's pretty easy because she won't jump after you solder that one. Now I'll go through, solder the rest of them in place. Same way. Now, as I may have mentioned earlier in this project, you could probably use perf board, this sort of stuff. And, you know, it's got copper pads on it, and you could conceivably solder these together onto those pads and then use short wires in between each of these to connect them together. I don't think that's really ideal, but if that's what you got to work with, go ahead and do it that way. The worst that's going to happen is it won't work and you're out a couple of dollars. And along the way you might learn something. That's not necessarily a bad thing, right? Now I will say also, I'd also like to comment that that tinning compound, or that chemical tinning process that I use, that seems to help with the soldering process sometimes. It just depends on the type of copper that's on the circuit board and probably how clean it is. I've had boards that are just pure copper, no tinning on it, and just had a bear of a time getting the solder to flow and work nicely, especially on perf boards. But with the tinning, this one is soldering up real nice. It's flowing and adhering nice to the circuit board material, so that's good. Now we'll be testing this in a few minutes, and you will be surprised as to how much light this thing's putting out. I've done a number of these types of lamps before, and generally I'm quite pleased with how well they work. Okay, all the LEDs soldered in place. Now I can turn my attention to the two 2.7 ohm resistors. And got the legs bent up because we're treating this through-hole resistor kind of like a surface mount resistor. Get a little bit of solder here to help use that as a clamp to hold it on the circuit board while I manipulate it and get it into place. And yeah, if you just saw me twitch, I burned myself with the soldering iron because I'm trying to do it left-handed, and, well, I'm not a lefty. Okay, and I'm going to wire on a couple of jumpers here so we can test this. Now, as will typically happen, I will get everything to work out great on the first one, which I did prior to this, prior to filming. And then this one won't work. And then you guys will have a good chuckle while I turn off the camera and then try to figure out what I goofed up. Alright, let's see what happens. Maybe we'll see some smoke and fire. That's always exciting. I just turned on my lab power supply, or my bench power supply, and I'm slowly bringing up the voltage. And I certainly got, oh, there it is. We got life now. Started lighting at around 17 volts. I'm up at 18.5 volts now. And almost 19 volts, and now I'm starting to pull some current. And I'll take it up to 20 volts, 20. I'm pretty sure on camera it just looks like a big white blob. This is 21.9 volts at a half an amp. Now what I'll try to do is I'll spin this around. Oop, I got to lift it up on my... I'll spin this around upside down and see if you can kind of gauge how bright that is by looking at what it's doing to my hand in that area. So now you get an idea of the brightness of this. Not a full idea, but it certainly throws or casts a tremendous amount of light from those 7 LEDs. And it's very economical for that amount of light. Now, in this particular project, I'm using a variable voltage supply for this, so I've actually got, we'll call it built-in dim control. So it's all around a very nice system for doing your custom lighting for various applications. Now, in a test I did earlier with the other board, I'm going to turn that down so I don't blind myself. I'll take it down to a dim glow. I ran it for a couple of hours and then checked it with a heat gun along the way. And at 22 volts, pulling a half an amp through the whole system, it barely got to the point where it was too warm to touch. I think it was registering roughly about 100 to 110 degrees Fahrenheit on my temp gauge. I then cranked the voltage up to around 22.5 volts, where I was pulling about 600 milliamps for the whole circuit board. And the temperature came up a little higher than I had earlier. I think 129 was the peak temp I could measure on either the front or the back of the board. So what I'll do, once it's in the enclosure, I'll do another test on that, because obviously we don't want to melt the enclosure and we don't want to melt the plexiglass lens on it. So we'll have to be careful as to how much voltage we put into it. But the whole system is rated according to the data that we found for these LEDs and the recommended resistors to get the current limiting. We're rated to run at a full 24 volts. Whether you need that or not, that's to be determined once it's in its intended application. With the circuit board made, that fits in here like so. Very simply held in place with 4 3mm screws. Now we're going to need to get power to this. So rather than try to make one of these, this is a purchase component. I'll be providing a link for where to get this. And this will go up through this outside hole here. It'll have a nut. Like so, and that'll be captive in that little hex-shaped indentation there. And then we'll just connect up these wires, allowing enough slack so that we got a bit of a service loop there. No need to have too much, but just enough so that you can get this out and maybe swap out an LED if one dies on you or something. So that's how we're going to get power into it. And then to seal the whole thing off, we need to have a lens for it, a cover, a clear plastic cover ideally, to let the light out. Let me show you how we made that. Now I'm going to turn my attention to making the lens for the lamp. The material I'm using is Lexan, and just pick it up at the hardware store. And this particular material is 3/32 of an inch thick, which is 93 thousandths of an inch, or 2.5 millimeters in the metric system. Now, there's a variety of ways you can cut this. You can score it, snap it. It's typical. You can do it a lot of different ways. Table saw, score it, snap it. I've got the CNC machine. It's a really easy program to write. We're cutting a rectangle and drilling 6 holes in it. Very, very simple program, but nonetheless, that'll be the process that I'm going to use. And to secure it in place, I'm going to use double-sided tape like I do with most stuff that I use or machine on the CNC router. And you can see the red lines here, and those represent the outline of the shape of the lens. And what that's helping me to do is to place the tape. I don't want the tape anywhere near where the cutter's going to cut. Double-sided tape, it can, of course, stick to the tool, and then that creates the chip sticking to it, and then the next thing you know, you got a melted ball of plexiglass on the end of your tool, and it can no longer cut. So I'm just going to put the tape inside that area and not cut through it. The other thing that you may notice, you usually cut plexiglass a lot faster than you would cut, say, or an isolation mill, a circuit board. And the tool that you're going to use is slightly different. And I'll show you that once we get over by the machine. You'll notice on this cutter, the cutting edges are serrated. And with those serrated flutes, you're going to get a lot smaller chips and so forth, but you're not going to get good chip evacuation, and you're going to get a lot more heat buildup. So these types of cutters are generally not very good in plastic. My preferred style is a very basic 2-flute helical end mill, and solid carbide. It's very sharp. But this type seems to pull the chip out and eject it much more efficiently, and I get a lot less chip welding. That's not to say it's not possible. It's very easy to get chip welding and melting when cutting Lexan. You just have to maintain a good feed rate and a good speed. If you go too slow, you're gonna melt. It's almost always better to just try to go too fast and then slow things down. I've got my material on my backer board here, my sacrificial backer board. I'm going to put some weights on it, let those sit in each place for a few minutes to make sure I've got a good bond between the plexiglass and our backer board. Along the edge you could see that the chips evacuated nicely and we didn't have any chip welding to the tool. As it got into the full width cut, you saw a little bit of stringing on there, and I got a tiny amount of chip welding. I use an air blow gun to try to push some of that away, and sometimes it helps, sometimes it doesn't. Now this was at roughly a 1/8 inch diameter tool, which is 3.5 millimeters, I believe, 3 millimeters, at 50 thousandths deep, which is about 1.25 millimeters deep. I kept the depth of cut shallow to aid in chip evacuation. Now we'll take it down to its full depth, cutting all the way through the Lexan. Now that last cut was at 35 inches a minute at 13,000 RPM, and that actually seemed to work out a little bit better. I've switched out the 1/8 inch end mill with a 1/8 inch drill bit, and now we can go through and drill the 6 mounting holes. Sometimes the chips just are stringy and they get wrapped around the drill bit, but they're not really welded there. You can pull those off easily after the spindle comes to a complete stop. Don't know why this is so satisfying, but everybody takes pleasure in that. Here would be one of our lamp housings, and our lens fits up beautifully. Now what I will do is take a sanding stick and break that sharp edge. And here is the lens. Now I'm just using basic Lexan for that. That'll be held in place with 6 3mm screws, and I may have a trick on how I'm going to deal with that for use inside the paint booth. So again, be sure to check out that project on our channel. So now we'll turn our attention to final assembly. Now, as mentioned, all of these holes are for 3mm screws, and they're already sized appropriately, but it wouldn't hurt, especially depending on how well your 3D printer prints, it may not hurt to run a drill in there of the appropriate size for a 3mm tap. Now normally you'd use a tap handle to screw the tap into the part to machine the threads in there. However, I'm a bit lazy, so I'm going to do it this way. Now to install our panel mount power connector. I got the nut in there ready. We'll get this pulled up so it's ready to engage the nut, and we'll make sure the nut is down inside that little recess, and we'll just start threading it in. And we'll snug it up with a pair of pliers. Now we'll trim these leads to length for soldering to our circuit board in this location and in this location. I've already got a dab of solder on the trace where I'm going to mount the positive lead wire, but I'm going to first tin that a little bit, make this go a little bit easier. And we'll just take this, and that should do it. Do the same thing for the negative lead. Now the one thing you want to do before you install your circuit board and screw it in place is to install your 4mm nuts in these mounting locations. Got nice little hex-shaped holes. We're going to drop the nut in there, get it to lay flat, and then put a drop of super glue on it to hold it in place. I'm using some 3mm by 6mm Phillips head screws, and we'll just screw that into the threaded hole we just tapped. If you don't have a tap, sometimes these will just self-thread and you'll be all set. Okay, we got our circuit board mounted up, our wires pulled off to the side. I think we're ready to put the lens on and go for a final test. Now with assembly essentially complete, I'm going to hook up my power supply, plug it in, and turn it away from the camera and away from my eyes, turn up the voltage, and at, let's see, right around 17 volts, it started to come to life. And as you can see, I'm up to 20 volts, there's 24 volts, actually 24.6 volts. And it's throwing a lot of light. Now what I want to do is I'm going to set it down at about 22 volts, which according to my testing earlier, kept the heat in here at about 110 degrees or so, Fahrenheit, not Celsius. So what I want to do, I'll leave this on. I'm going to monitor temperature using this device. Probably not the best device, but it's the only one I got, so we're going to try it. And I just want to make sure it doesn't get too hot now that everything is closed up in here. So I'll monitor that, and then if the temperature gets too high, where this plastic softens up, I'll have to dial back the voltage to a point where everything kind of comes into balance, where I'm getting enough light, but not so much light that it's generating so much heat that it melts the plastic enclosure. From there, I can mount that up in my cabinet, and I've got a very cool shop light, or a very cool light for my paint booth. All around, I'm thrilled with how the project came out. The LED lights really give a nice illumination inside the paint booth. I've also come up with a way to help protect the lenses from getting coated in paint. I just applied some clear contact paper on them, and then once they get covered in paint, peel off the contact paper, put on a new piece of contact paper, and you're ready to go. So with that, that concludes this project. Hopefully you really enjoyed it. If so, make sure you subscribe and give me a like there. And I look forward to seeing you in the next project. I'm Chris DeHut for Making Stuff with Chris DeHut. Thanks for watching.